So for the next few minutes, we'll be talking about one component of standardized electrofishing sampling, something called output goal tables. And it really gets down to this fundamental question of, given my equipment, given the environmental conditions I'm faced with and the fish I'm after, where do I set the dials? So what we're going to do is discuss the development and use of electrical output goal tables for standardization, and we're going to have some support of that by visiting a community of practice website called electrofishing.net, which, taking the long view, might be the most important thing you take out of this seminar. And then from there, excuse me, we'll be talking about waveforms, their characteristics and fish catching attributes, and finally development and use of output goal tables. So the first thing we're going to do is talk about, go over electrofishing.net. I want to show you, bring that up now. And so this is the website, electrofishing.net. And I want to page down here slightly on the home page, and you'll see here that there are several links to training, tools, research, buyer's guide, and blogs. So with training, let's click on that, and you'll see that a page will come up, and there's a safety PowerPoint presentation. There's information on taking an online safety course, which is newly revised and free. There is Electrofishing Essentials instructional videos. So I'll click on that at risk of and show you those. And this is about actually about 6 hours of instructional videos on various topics, including the one we're talking about today. So to let you know that those are also, of course, free. You can take training online, principles and techniques of electrofishing online, and then finally there's advanced training in person from Smith Root and our principles and techniques of electrofishing fish and wildlife service in person, a 4.5-day course, and then courses from the Northwest Environmental Training Center. So I wanted you to be aware of that. Let's take a look at tools real quick here, and just let you know that there's a resources page that links to our online course information, and I'll click on that, and you can see that there are PowerPoint presentations or manual chapters, you want to look at it that way. There's various protocols, programmed Excel files. In fact, one we're using today is this one here, this EF Goal Power that we'll be using at the end of this presentation. So that's all there for you. You can get that later. Now, also I'll say that there's a buyer's guide, so if you're interested in, well, eventually will be, buying a piece of equipment, there's a list of considerations that's written here that you can mull over to think about your specific situation and to try to guide you to making a good choice. And then we have some suggested, recommended models from some companies, control box models, backpack models, that sort of thing. Okay, and finally, there's a blog, and this particular blog that I published last month basically goes over what we're going to talk about today. But these blogs are put in chronological order, but they're also categorized up here into these various classifications. So for instance, if you go to the video part, there's some instructional video links. We'll look at that. And here are links to various videos, including Electrofishing Essentials that we just looked at a minute or two ago. So that is electrofishing.net. One other thing I will show you, I'm going to go to the home page. And actually, let's see if I go back. I don't want to And we'll just try it. There it goes. Okay. So at the very bottom of the home page here, there is an electrofishing app that you download to your phone. Excuse me. Download to your phone. And it doesn't require internet connection in the field, but basically what it'll do is help you to determine what settings you should be trying at your location. So I'm going to click on this View the Mobile app. It's a web-based app, but this is what it would look like on your phone. There's information on backpack standardization, boat standardization, a little bit on electrofishing safety, some references. And then there's standardization calculators. I'm going to click on one. There's a bit of verbiage here about these calculators. If we go to the calculators, you'll have three calculators. One is that deals with converting specific water conductivity to ambient, if that's because ambient is what we are after in electrofishing. A current goal calculator and a voltage goal calculator. So I'm going to just click on the voltage goal calculator, and we'll come back to this at the end of the presentation. But basically, you input some threshold information that you get from the literature or some that you can get from electrofishing.net or your own, hopefully. And a fish conductivity value, which also can be from the literature or your own work. And then basically, once you've done that, you have the site ambient conductivity. So that's your sampling site. So what is the ambient water conductivity, your sampling site? You put that in, hit the calculate button, and in this case, you'll get a target voltage to shoot for. So that's that. We'll come back to it at the end. Okay, so that's electrofishing.net. Now I'm going to talk about electrical waveforms. And there's three main types: direct current, or continuous, or smooth DC. It's called the most common kind, pulse direct current. Many forms of that, and alternating current, AC, the kind that comes out of your wall sockets, and there actually are many forms of alternating current as well. So direct current we'll start with, and basically this graph is like any graph you get off a Scopemeter. The y-axis volts, and the x-axis time in milliseconds. And so if you're using direct current, at some point you turn the switch on, and the waveform goes up to the set voltage, output voltage, and then continues along on a straight line. Now, with direct current, the fishes are responding to peak, which is the top of the waveform here. And average voltages, or average power, average current, those deal with equipment capacity. So for fish, we're on the peak side. For equipment capacity, we're on the average side. But for direct current, they're both the same. There's no, the average and the peak are the same. So this was, but we always talk about it as peak voltage or peak current. Again, and if you were to plot current, it would have the same pattern as a voltage on a Scopemeter graph like this. Okay, so what are the advantages? The advantages of DC typically causes attraction to the anode, and that attraction can be unbelievably strong. Also, it's often less injurious to fishes, especially with trout and salmon. Here's a screenshot from a Scopemeter, and just to orientate you to that, again, the Scopemeter has a grid and basically a y-axis and an x-axis. And the y-axis volts and the x-axis in milliseconds. And you can change the scaling. In this case, each vertical division is 50 volts per division going vertically, and horizontally, each division is 5 milliseconds per division, kind of a common thing. So the 0 volts baseline, this current is on, this direct current is running, and the 0 volts baseline is here denoted by this black rectangle, and the waveform has been turned on and has jumped up to this level. And we see the readout is 194 volts, and this symbol is peak, so peak volts. And if we look here, we can see that the 0 volt baseline started a little bit below this grid line, division. But let's just go count 1, 2, 3, 4. So about almost 4 divisions high, 4 times 50, 200 volts. So that's how this is read. Okay, so a lot of times you have a ripple on top of the DC waveform, and sometimes it's like sawtooth, and it can be pretty accentuated and not just smooth, but ripples. Some manufacturers think that helps with fish capture. I don't know if that's the case, but oftentimes we do see a ripple, and how that occurs is, and we'll talk about this a little bit later, but you fully rectify AC waveform, which basically means the negative excursion here. An AC waveform is a sine wave, goes positive and negative. Well, the negatives are flipped up, and so you basically have this rectified AC or pulse DC waveform, and then you run it through a transistor, and you smooth out this pulse DC. So you get this. The red is the smooth DC ripple, and it's always on. It never goes down to the 0 line. So it is a direct current waveform, but it has a ripple to it. Okay, what are the drawbacks of DC? Well, it may require slightly higher amperage than pulse direct current for successful electrofishing, and it's definitely more energy consumptive. It's like a flashlight that you have turned on all the time. It's always on. So it's 100% duty cycle, means on all the time. And that means that you're restricted to a narrow or conductivity range. So, for example, we had the opportunity to fish with the Ashland office up in Lake Superior a couple years ago, and we estimated that the conductivity range for using direct current was 35 to 320 microsieverts per centimeter, using a classic 2-boom metal hull boat with droppers and an infinity control box. So that's a lot narrower range than you would have with pulse direct current usually. And DC is not available in all models. So what are the fish catching considerations? Well, the frequency has no application because DC is on all the time. Duty cycle is always 100%. So there's really few adjustments. You get just a smooth DC or a ripple type DC, that's about it. And so your adjustments are voltage and amperage. And basically what you do then is you build and use these volt amp output goal tables for just this, DC waveform. So it makes it fairly simple to get your head around. Now we mentioned output goal tables. I want to throw this up just for a second, a little peek into the future. But this is what one looks like. And so these output goal tables are predicated on a number of things. One is the equipment. So this is backpack, a waveform. This is pulse direct current, 60 hertz, 25% duty in this case. An electrode arrangement, a resistance of that electrode arrangement, something called a fish conductivity that we're going to use, and also really stream size or lake type, shallow cove versus steep-sided, large river versus medium-sized stream, that sort of thing is specific to those water body types, and also can be specific to target species if you're going after particular species or assemblages. So that's what how one looks like, and basically pretty simple. You have a table or that phone app, and you go out into the field and you take ambient water conductivity, and let's just say your sample site, conductivity, let me go back here, sorry, was 150 microsieverts per centimeter. Then you say, okay, what's my target voltage? Well, my target voltage was 211, so I want to dial that to 211. Or my amperage goal is 1.15 amps, so I change the voltage to get to that amperage reading. But so that is how these things work pretty simply. You just take the water conductivity, look it up on the table, and then check what your goal should be, what you should be shooting for. Okay, next waveform, pulse direct current. And we can see that it's a lot more complicated than just DC. And so we have this pulsing where we have the waveform at 0 volts, then it turns on, goes up to some output, a peak at the top of the waveform, and it runs for a certain amount of time, a pulse width, and then it comes down to 0, is off, goes back on to some output voltage, peak output voltage, exists for a few milliseconds, back down to 0, and on and on. So pulse, pulse, pulse. So the pulse is a part of the waveform during which the voltage is present, right here, right here. Pulse width is just the time the pulse is on in milliseconds. Some oftentimes see 4 milliseconds, 5 millisecond pulse width is common. Frequency is the number of pulses per second. Now the period is that time from the beginning of one pulse here to the beginning of the next pulse. So this, denoted by T, this is called the period. Now the duty cycle, that's just the percent time on. For DC, percent is on all the time, it's 100%. Now for this waveform, it's something less than 100%. And how we figure it is we take the pulse width in time divided by the period in time. So how much of this period is taken up by voltage present. So in this case, we can kind of eyeball it and say, well, it looks like that this is about a 50% duty cycle because the pulse width is about 50% of the period. The other thing I will say is that the fish are looking at peak. And so a lot of these meters now you see are peak reading meters, but some of the older units might have average. And so particularly with amps. And the relationship of this is just by duty cycle. So if you have a peak reading and you want to know what the average voltage is, you just multiply the peak by the duty cycle. So let's just say the peak is 100 volts here, and you have a 50% duty cycle. So 100 times 0.5 equals 50 average volts here. Some people it can be a freak out for some folks when they're changing from, say, a GPP type unit, which has average ammeters, to some kind of another control box that has peak, and they're used to 3 or 4 or 5 amps sitting on their amp meter, and then when they get out into the lake and turn their unit on, all of a sudden they're 20 amps, and they think they're going to blow things up, but that's just because they were using, maybe a 20% duty cycle, and so the peak's going to be 5 times that of the average. Okay, advantages. Well, there's many waveform options, many combinations of different frequencies and duty cycles. So you got a lot of experimental room in there. Pulse direct current may cause attraction to fish the anode, but not as obvious as with DC. Lamarck actually called it a pseudo attraction. And it's much less demanding, pulse direct current much less energy demanding than DC, and that's why it was developed for electrofishing. So it can be applied, that pulse direct current can be applied across a broader water conductivity range, and it's generally more effective for capturing smaller individuals than direct current. So here's a Scopemeter screen of a pulse direct current. We call it a square wave because this looks more like a rectangle, but we call it a square wave because the corners are squared off about 90 degrees. So that's why we call it a square wave. So we can see that the voltage going along at 0. There's that little rectangle. It goes up to some voltage output, exists for a while, and then comes back down, goes along at 0, comes back up, depending upon the frequency. So basically, the divisions are 5 milliseconds per division, so that's 5 milliseconds across, and each dot then is 1, 2, 3, 4, 5. Each dot is 1 millisecond in length, so in time. So we can see that this particular waveform is about 4 milliseconds wide. It also is about 4 squares high, which is 50 volts per division, nearly about 200 volt peak, and then we have that automatic readout here. And also we have a duty cycle readout. Percent D is duty cycle 24%, which basically is saying that this pulse is about 24% of the period. So it's on, the electricity is on about 24% of the time. Okay, so one thing I wanted to show you is that when a unit becomes loaded up in high conductivity water, that oftentimes these waveforms will go from kind of a square wave to to somewhat of a spiked waveform or slanted waveform. So we see here on the left that we're applying 49 volts at some water conductivity, and then we start increasing the voltage quite substantially, and you can see that the waveform is is slanting, is deforming some. So how do we measure peak voltage on these? Well, by convention, we measure peak voltage where the waveform first becomes about a millisecond wide. So that'd be about right here is where we would measure that. So sometimes our meters on our machines will disagree with our Scopemeter measurements because the meter on the machine may be reading that top piece right there, the very peak, and we're usually do about where the width is about 1 millisecond. This is an example of Scopemeter tracings on a backpack shocker going from 10% duty cycle on up to 80%. So 80%, nearly the whole period is taken up by the pulse. Okay, this is a pulse direct current, but it's rounded waves. These are mostly limited to GPP units and Type 6 models from Smith Root. Basically, we call them rounded because they are from a rectified AC waveform. In this case, this is half wave rectified. One thing about rounded waves is that they seem to take more energy, more power to do the same amount of work than square waves do. So they're less efficient in that way. So an example is you have alternating current coming in, sine wave coming in from the generator, pass it through a diode, it clips off the negative excursion here and leaving you with just positive above zero voltages. So that's half wave rectified DC, and that's how those waveforms are generated. Especially pulse DC is something called a gated burst or a complex pulse system, or you see pulse trains, other terminologies for this. And basically, this was developed to try for salmonid and trout work to try to catch them efficiently, but yet lower their injury rates. So especially in salmonids, frequency is a main offender. The higher the frequency, at least up to 120, the higher the injury rates in salmonids. So what the idea was is that we'll fool these fish and we'll say, okay, we're going to put these pulse packets out, and these pulse packets mimic a pulse, and they're coming in at 15 pulses per second, say, pretty low. And that is not very efficient for catching fish. Doesn't injure them very much either, so that's good, but I can't catch them. So let's hide some high-frequency pulses that may be 200 pulses per second on a frequency inside these packets. So basically, the catching part is inside the pulse, and the injury reduction part is the fact that these pulse packets are at a low frequency. One thing we know for sure is that we need to use more power with this waveform than a typical standard pulse DC to catch fish. It does oftentimes result in lower injury rates, but and I will say that this type of gated burst, this waveform, has been used in streams, just on warm water fishes, and some folks really like them, so it's something to keep in mind. I want to bring it up. Okay, what are the drawbacks of pulse direct current? It often does not cause attraction, And before I said this was an advantage of this infinite number of waveform options, but it's also a disadvantage because it can lead to the use of suboptimal frequency and duty cycle combinations, which I've seen on more than one occasion. It may cause a high rate of trauma. So for salmonids and trout, typically use 30 pulses per second or less, and it's usually not as effective as alternating current, AC, and very low and very high water conductivity. Okay, so the fish catching considerations, we get frequency, duty cycle, and then voltage and amperage. And so basically for the frequency part, 60 pulses per second or 120 pulses per second seems to be optional for general catch efficiency. Higher frequencies, 120, are better, typically for capturing smaller fishes. Now, if you're using a GPP unit, oftentimes people use 120 pulses per second because that's the frequency range that allows them to have a quote-unquote robust duty cycle. And that's a topic for those electrofishing essentials. If you want to look at that in those, there's a presentation on GPP unit output. Okay. Lower frequencies, as I said, 30 pulses per second or less, used on salmonids, reduce injury. Low frequency, 15 pulses per second for blue and flathead catfishes, and moderate conductivity. Now, something really interesting, in very high conductivity, like near estuaries, pulsed AC has been found to be effective. Now, there's only one unit I know that puts out actual pulse DC, and that's the Infinity box from Midwest Lake, and that actually pulses AC. And researchers in Virginia on those tidal rivers found that when pulse direct current, low frequency pulse direct current didn't work, they used 15 pulse per second pulsed AC and really were very effective on channel catfish. Okay, in colder water, higher frequencies may be more effective on blues and flatheads. So that's the frequency part. Duty cycle range for general catch efficiency is 20 to 40%. Now you can go down to 15% if you're in high conductivity and you need and you're loading your machine without much loss possibly, but 20 to 40% is in the zone, and basically 25 to 30% is a sweet spot in general. So so that's the duty cycle stuff, and then build those volt and amp output goal tables as guidance for your settings. Square ways typically need less power than rounded ways, and gated bursts were developed for reducing injury in salmonids. So there we have it. So last one, alternating current, AC. And alternating current is alternating because what it's doing is we have a positive voltage and then across zero negative voltage, and then a positive voltage in a sine wave. So what this means practically in the field is there's no constant anode or cathode. So at one instant, your booms on your boat are the anode, and your boat hull is the cathode. And in the next instant, the booms droppers are the cathode and the boat hull is the anode. And that switches back and forth at the frequency of the generator of 60 times per second. So with AC, we also have voltage peak. We have this peak voltage, but in addition, we have also a peak-to-peak voltage. So that's denoted here, VP to P, right here, peak to peak, so much higher. In this case, would be double, peak-to-peak voltage would be double the peak voltage. And then classically, when we talk about AC voltage or AC current, or AC power, we're talking about RMS, root mean square. And on a perfect sine wave, root mean square is about 70% of peak. So you're typically, if you have a unit that uses AC and you have an output gauge, a meter, like a voltmeter, it's going to be giving you RMS voltage. Now, if you want to know what the peak is, which is what the fish are interested in, or affects the fish capture, then you can do a quick little mathematical change, say RMS times 1.41, which is the inverse of 1 over 70. So RMS times 1.41 equals voltage peak. The breakdown is that most of the time, almost all the time, you don't have perfect sine waves, and so the relationship between RMS and VP, peak voltage, is not constant, and so that's an issue with metering for sure. So advantages for AC can be effective across a broad conductivity range, more effective than pulse DC and very low or high conductivity. And why is this? Well, in low conductivity water, you need a lot of voltage. You need a lot of voltage to push the amperage out. So remember that AC has peak-to-peak voltages, and so they can throw a lot more voltage out, and so you can be successful in low conductivity water. Now, in high conductivity water, you need amperage, and so likewise, that sine wave has a peak-to-peak amps as well, so you get more amperage out in this high conductivity water situation. Here's some examples of alternating current from various backpack units, or various units, I should say. The infinity box will pass through basically the generator sine wave here, but that's fairly rare. Usually you get something more like this. It's an AC waveform because it does have positive and negative excursions, but this is fairly common. But that's how it is in backpack with electrofishing units, and that's why RMS and peak does not have a relationship you can count on. Okay, the drawbacks. Doesn't cause a traction response. There's no way a fish can keep up with an anode that's changing 60 times per second. There are many AC waveforms actually, and these forms are specific to particular models, so that can hurt your fleet standardization unless all boats or backpacks have the same model control box, if you're using AC as the waveform. As I said before, most voltmeters display RMS voltage or amperage, and it's okay if it's a full sine wave, but that's usually not the case. So this relationship of peak voltage equals RMS times 1.41 is really not very common one that you're able to use. You can't use it. And so therefore you have to monitor, if you want to monitor your peak outputs, which is what you're going to be interested in if you're monitoring AC, you have to use external metering for that. Not available in all models, particularly backpacks, and may cause a high rate of trauma and injury. All right. Fish catching considerations. So again, some units have one form of AC, others have the capacity to change the shape of the waveform, actually, through changes in duty cycle. And so when you build your volt amp output goal tables for AC, you got to remember AC is just not AC. There's particular forms of it. You build it for that particular form. Of course, that's the same with pulse DC because these tables are built on a frequency and duty cycle type criteria. Okay. And most likely you'll need external metering if you're using AC to monitor boats or amps, peak boats or amps. Okay, that's it for the waveforms. Let's get into this output goal table stuff. And so what's the idea of standardization? Well, it's to reduce the variability in catchability, in fish catchability. That's Q. And that's because, if you can take that variability, reduce that variability in Q, then that helps your catch per unit effort data track, say, population trends more accurately. So there's various components to standardize by. These include gear type, electrode design, what waveform are you going to use, even crew number, crew experience, dip net mesh size, sampling design, day or night, for instance, environmental conditions, temperature. We don't fish unless the temperature is X amount or above, or discharge. We don't go out if discharge in the stream is above a certain level. And electrical output, which is what we're going to be talking about. So the standardization aspect we're going to talk about are these output goal tables, and they can be peak volts, peak amps, and they can be peak power tables. And they're used as guidance. So you can look at these output goal tables in two ways, and they are looked at in two ways. One is that when you go out and you have a table and you take conductivity measure and you find the voltage or amperage you're going to use, that's what you use. You put that voltage or amperage on output, and you start fishing your sample site, and that's that. Other folks uh, may say, well, look, I'm just going to use this guidance. So I'm going to take water conductivity, I'm going to see what my target is, and then I'm going to do a little trial near my sampling site to see, to fine-tune my output. Usually with these goals that you have to adjust upwards slightly if you're going to adjust. So there's two ways of looking at it, and looking at these tables as strict orders or as sort of a guidance. And I think main part of that is how much do you put in to developing these output goal tables, how much trust do you have in them. Okay, as I mentioned before, output goal tables are specific to gear type. They're specific to electrode design, waveform, target species, or whether if you're fishing assemblages, and water body type as well. So, and just to let you know that these output goal tables are based on the power transfer model of electrofishing, and they require input of something called threshold data. And this threshold data is pretty minimal, but it is the minimum voltage or minimum current or power needed to successfully sample a water body. And that's your threshold data. And you have associated water conductivity with that minimum voltage or current, and you have an estimate of fish conductivity that you get from the literature or from your own work. Now, if you're saying, well, how do I understand, how do I get fish conductivity? There's a lot of blogs on electrofishing.net on how you set that up. So I keep referring you back to electrofishing.net in particular to some treasure trove of information. Okay, so inputs to build these tables, we often use a fish conductivity of 115 microsiemens per centimeter, but what we've seen, fish conductivities that vary from 80 to 150, like that. 115 seems to be a pretty good, if you don't know, seems to be a pretty good figure to use. You should obtain your own threshold data if possible, and develop your own tables. And we're going to use an Excel file called Go Power, or you can use the Electrofishing app. And we'll talk about protocols for gathering threshold data. Now, you might say, well, I don't have any threshold data. I don't know exactly how to get that. So we do have some suggestions to start with, and all these outputs are at 115 microsiemens per centimeter. So, for instance, we're saying that a backpack with a ring anode and a rat tail cathode, that your threshold settings are 1 amp or 240 volts at 115 microsiemens per centimeter. So that's your threshold information. And you can see there's others for barges, boats. And Jan Dean has a blog in electrofishing.net that has these values and more for other pieces of equipment. So here's your threshold information. If you want to use this, by all means, I would suggest do that and then go out and test these tables. So, and you might find these tables may not be accurate, so try these threshold values we suggest and see how they work for you, and then modify and adjust as needed and build your own tables. And we certainly appreciate your feedback on these experiences. Now, I want to say that if you have a fleet of boats that you're trying to use one table for, or a fleet of backpack units or whatever, that amperage is by far the best output to use for standardization. There are a bunch, and Jan's got a number of blogs on that. If your electrodes, all boats, an agency might have a set of boats, and they say they have the same electrode design, but we hardly ever see that they do. They're always a little bit different, but they might all be drop or Wisconsin-style rings, or they might all be Sears or something. But as long as you got fairly similar electrode design, say on a boat, I might have 4 droppers, and he has 6 droppers, and she has 5 droppers, then you probably are okay with using current. Voltage would be different; it would vary. Now, if you're in low conductivity water, which is very voltage, when voltage is a quiet response variable, or if you're using really low power units as backpacks or both, voltage may be a better choice to use. But just be aware that voltage is harder to use as a table across different equipment types. So current if you can. Okay, so let's make some tables. So what I'm going to do now is I'm going to bring up EF goal power for you. And basically, we're going to have two tabs. We're going to look at a current goal and a voltage goal. And basically, what all this is, we have an ambient conductivity calculator, just like you would have in the app, electric tool app. And all this does is, if you have specific conductivity and a temperature, then water temperature, then it'll give you your calculate ambient conductivity, which is what you're after. So say your specific conductivity was 500 and your temperature was 15 degrees, then your ambient conductivity is 400, and that's what you would look up down here for 400. So so the rest of this, besides the calculator, you have input, and that's the green box. If we input your threshold information, and then you have an output table, output goal table, voltage goal in this case, and a graphical depiction. So let's just say we had that backpack unit, and if you remember, we had 240 volts were needed at minimum for 115 conductivity. Fish conductivity, we leave at 115. You hit the button and you return, and there you are, and that's it. So here's your table here, and here's the graphic that describes the table. As you can see that in low conductivity water, 100 or less, you really start needing the voltage goal. Now, say you go out and you go, well, my conductivity is 232. So you can just go into this and put 232 somewhere and just key that in, and there's your voltage goal. So if you're out with this threshold information and you're out at a stream and you had this table and you said, okay, my conductivity is 232, I put that in, and my voltage goal is 179 volts. Now with current goal, let's say we're in a boat, and oftentimes boats have, for square waves, 10 to 12 amps at match conditions, or 115 we're going to call it. So let's do a boat. So in this case, so amps, so I'll just say I need 10 amps at 115 microsiemens per centimeter. Fish conductivity is 115, and then we have our table, our amp goal table there, and our graphical depiction. One thing you also notice is that the amperage goals are linear with ambient conductivity, and that's also what makes this nice for standardization, is you have this nice linear relationship between the current goal and conductivity. So that's how this works. You can get those in the course resources page I showed you. A link through electrofishing.net, or I'll send this to Candace too, so you can get this particular file. So finishing this up, let me go ahead and start back here. And so here's the protocols to use the tables and samples. Just a couple more slides here. So you get out there and you measure ambient water conductivity, or if you have specific conductivity, you need water temperature, you convert to ambient. And there's blogs on that. Imagine that. Deploy your electrodes in a fishing fashion within typical habitat conditions. So for backpacks, we suggest employing your electrodes as you would. So if you have a rat tail cathode and an anode, handheld anode, you put the handheld anode in front of you, you extend the rat tail behind you, and stand at about 1 to 1.5 feet of water. You look at the goal table to see what your target voltage goal is, your target amperage goal. And then if you're using amperage, then someone with the operator standing there with electrodes deployed in 1.5 feet of water for backpacks, adjust voltage until the current goal is reached as you see that on your peak ammeter. If you're using voltage, they just adjust voltage directly until the voltage goal is reached as indicated on your gear's peak voltmeter. So that's really important to have these meters and ammeters on your backpack unit. And I do want to say real quick that don't get confused about voltage setting and voltage output that may not be anywhere near the same thing. So if you put on 100 volts on your unit, you may be getting 56 volts out. You don't know. It's not important your setting. What's important is what you get at, what you're getting out, and that's what you key in on. So also, anyway, so you put your voltage on, your amperage on, you get your goal, you get your amp goal on there, your volt goal, and if you have time to run a trial test, you go outside but near your sample area and just see how you're doing. If it's not very, if you see a lot of escapement, then you can adjust settings. And so you once you get out there to learn, you want to record a few things like ambient conductivity, your threshold voltage or amperage used. It'd be great if you record the major reaction of fishes. Is it inhibited swimming? Is it getting good attraction? Is it mobilization? And then optionally record your assessment of the quality of the sampling. So this way you can look back on your records and kind of get an idea of what happened. You can learn that way. And that's what these meters do for you on these units. You have good metering. It allows you to learn. Now that's how you use it, the table. But if you're collecting your threshold data in the last couple slides, what you want to do is you choose a waveform, whatever it might be, and you choose your gear type and electrode configuration. It might be pre-positioned area shocker, it might be a backpack, whatever, raft, barge, anything. So you determine what you're going to use, the waveform, and you get out to your sample site. You take ambient water conductivity, you record that, start a low voltage setting, and begin electrofishing and see how, note fish reactions, and you go, okay, is this successful, unsuccessful? What am I seeing for fish reactions? If it's unsuccessful, you start a low voltage, so you're going to be probably unsuccessful to begin with, and you then increase the voltage. If you're satisfied that that particular voltage level for that waveform is not working very well, you increase the voltage by some amount and go through that again, test it again, and see until you get this lowest voltage or lowest current, if you're getting current too, that are found to result in successful electrofishing. That's your threshold. Now, and this is important. Once you've determined your, I'm underlined candidate threshold settings, your candidate, then what you do is then increase voltage. Stay out there and increase voltage another 25 or 50 volts. And notice sampling is the same. If it's better, then your initial threshold was too low, right? But if the effect appears to be the same or eventually even declines, then use your original threshold estimate. So I think, that we're looking for the threshold minimum voltage, minimum amperage you need for successful electrofishing. And I think as you turn the voltage amperage up, there's this zone of equal fishing, but then you can overpower, actually, and I've seen this, you can overpower a sampling area and actually your catch rate declines. So also want to mention that if you have a couple candidate thresholds and you notice that they seem to fish similarly, but one results in a lower fish recovery time, then maybe you want to go with that. And so you can tune your threshold a little bit with fish welfare. Now, if you're unsuccessful in the first attempt, just go in reverse. So you say, oh, I'm really successful. I got to reduce voltage more, and then go down to you're unsuccessful and then come back up. And you may not get to successful electrofishing, and that's when you have to change your waveform type, or if you're using pulse direct current, maybe you need to up your frequency or change your duty cycle and start over with low voltage settings. So, and then finally, last slide, once you obtain successful electrofishing, when you're out there getting this threshold data, record these things because they're quite important metadata. The ambient water conductivity, the gear type, voltage setting, but more importantly, the voltage output on the meter, the current output on the meter, waveform types, the fish capture prone response, and very importantly also water body type and size, because we build these, we're seeing a lot of really cool consistency for boats and for backpack units, say, but we're not sure in backpack units when we say, well, this is for medium-sized streams, this particular table, what exactly is the dimensions of a medium-sized stream? So, and what's a small stream? And that's the kind of information that is really going to help us that we don't have a lot of. Right now, I can say that a medium-sized stream, talking 5 to 10 meters across, and a small stream is something like a meter, but that's about where we're at with this, and that's where we need the input from you all. And just the last thing, the water body type and size, like for a stream, mean width and mean depth if possible. So anyway, Candace, that's to the end of the slides. And let me do one more thing. I'm sorry. I don't know what the time is, but by golly, we're going to keep going just for a second. Let me hit the escape button. There we go. And I want to bring this back up, this voltage go count. This is what you see on your phone. So let's say we're using backpack unit, and we're using the suggested threshold that we have in electrofishing.net, and that's 240 volts, the test ambient conductivity 115 with a fish conductivity 115. So we're out somewhere. Let's say we're at a very low conductivity area we're fishing, and it's 53 microsieverts per centimeter. So we'll put 53 in. So that's our site. This is our sampling site right here. And I'm going to hit calculate. Our target voltage then, 380 volts. So I'm standing out there. I take ambient conductivity. It's 53. Given my backpack shocking, given those threshold figures, that says my target voltage is 380. And I put 380 on there, deploy the backpack unit, and a foot and a half of water with electrodes, a radius if I was fishing, turn it up to 380 and go for it, and see how that works for you. Anyway, so there is absolutely the end, I promise.